Welcome again to the NPTEL course on storage systems. In the previous classes, what we were doing was to start from, let us say, the lower device level, and we were trying to move upwards. I mentioned earlier that we can become a very high level, extremely crude characterization as devices, protocols and applications. So we had a look at the devices a bit, then we introduce the SCSI protocol, and then if you have multiple devices to be accessible, we try to understand how to use SCSI to do it. And so we'll discuss a bit about the fiber channel protocol and how it can be used to design to use it in a SAN. Today what I would like to do is to slightly go up the chain. We start looking at how files can be served across, let's say, multiple devices, across multiple systems. Okay. So today we'll talk about some aspects of network file systems. Again, let's make some comparison between the two ways of thinking about the problem. The one is the approach, what is called the storage area network approach. The other one is the network attached storage approach. In the SAN approach, basically the abstraction is a raw block device. So because it is operating only at the raw block device, it means that we can only refer to blocks with numbers. That means that there is no user let us say understandable name for this storage. Whereas in a network attached storage, we are now, instead of talking about raw blocks, we are starting to talk about in terms of files. Okay. And the file abstraction is well known, so because it's well known, it is slightly more convenient. In a sense, NAS is easier for the user. SAN is a bit more, let us say, a bit too difficult to use as of now. Now, the access model is for the SAN is SCSI command set, and we looked at some of this some time back. Whereas for NAS, it's going to be file operations. The only issue is this, as we discussed earlier in the very beginning classes, these file operations are now going across the network, and because they are going across the network, the kind of semantics that was possible in a single system may not be possible here. It is going to be more complicated. Essentially, a lot of consistency issues show up, and so it is a more tricky thing to provide this kind of capability. Okay. The consumer in a storage network is typically either a file system or database, and whereas in the case of a network attached storage, usually most applications are written assuming the file abstraction. Therefore, applications, for them it is quite appropriate. Whereas the other possibility is the database also might use a NAS, because database also might find it easier to manage things if it goes through various file abstractions or tools available for managing file systems. Okay. That is why NAS is somewhat more popular, because it's easier to manage. Whereas for SAN, you need to have specific tools which are highly specific with respect to the type of SAN you have. Again, when it comes to naming the flows, for example, or you need to have in SCSI, as I mentioned, it's going to be a initiator, target, and the logical unit. So this is the thing that is going to be used for connecting up to entities that are involved in storage transfers. Whereas in the case of NAS, you are operating at the level of, let us say, some file systems are getting exported, and they are being, let us say, imported into some file system on the client side, and so they need to have some way in which you can refer to those file systems that are being exported by the server. Okay. So, and normally you will use IP based methods, for example DNS, to figure out how to talk about a server, etc. Okay. In the Windows world, you use slightly different model, the bins model for name lookup, etc. For SAN, typically, as we mentioned earlier, SAN devices were designed assuming that it's operating in a data center, and therefore the security has been relegated to the transport layer. Okay. There's not serious security at any of the lower levels, it's all at the higher levels. Okay. In the NAS case, you are going to have at both the transport level as well as at the file system level. Okay. Whatever file system provides you, that also is possible. Okay. And it also is possible at slightly different levels. For example, typically when you are making storage requests, you might go through some infrastructure called remote procedure call, RPC. It might have its own methods, and that might also be an issue. So we have to look at the security could be given by that particular aspect. And another important issue, I think, which is not listed here specifically, because we'll go into detail much more in some depth, the consistency issues. As I discussed it in the previous class, storage network in its simplest form or its most basic form assumes that there is only one party which is accessing it. Okay. Whereas since the NAS you are at the file system level, usually file systems, especially the Unix variety or the more including the Windows variety also, they have a notion of multiple users, and therefore there is already some infrastructure for making sure that there is some security of one user from the other with respect to let us say readability or writability. Okay. So in a sense, the NAS basically excels with respect to providing some model about sharing. SAN actually it has to be retrofitted on top of it, or some applications that agree between themselves how they're going to do it. So there are other differences, but I think I listed some of the more important ones. So if I look at NAS, why are they required? I think basically because of multiple reasons. As I mentioned, one of them is for sharing purposes, because the file system is in the picture, therefore sharing is much more easy. It is for consolidation, basically because you can have multiple file systems on a server and you can put all of them together in one place. And I mentioned already that databases might find using the file system as a way to manage its resources much more easy than otherwise. Okay. And the other requirements like performance, resilience, scalability, manageability, all of them may be slightly easier and sometimes and slightly more difficult because of the kind of file model that we're going to use. Because if you take the file system model, it might have its notions of how to provide performance or resilience, which may not be the right model if you integrate multiple things. For example, if you take a single file system, the performance is improved by caching, etc. Whereas when you put multiple file systems together, multiple nodes together, then it may be that the caching entails some aspects of consistency, which may become problematic. Okay. So there are issues that we have to resolve. Okay. So fundamentally, as we discussed before, in NAS we have file level access, it's not block level access. In Unix it is NFS, in Windows it is something called CIFS. Okay. So basically what happens is, on the client side we have what are called IO redirectors. What are these IO redirectors? They basically take the typical model in Unix is that they can have multiple file systems on the client, and each file system is abstracted by the kernel, so that the kernel only needs to talk about virtual file system operations. Okay. So the kernel interacts with all the file systems through what is called a file system independent layer, which is called the VFS, virtual file system. And similarly, each metadata that a file system keeps for a file, what is called the inode, the kernel keeps something called the vnode as its representative, so that it can deal with all the different files in different file systems in a uniform manner. So Unix has this notion of BFS/vnode framework. So basically, when a request comes in from an application on a client, it will do something like a read or write call. It first navigates through the file system independent layer, the BFS vnode layer, and that's on the client, and that has to be now transmitted to the other side, the server side, where it actually meets the real file system. So basically, we have the BFS vnode framework that is basically used as a way to interact with the remote file system. So that's why I'm calling a redirector, because it is from the client side, the request actually has to be redirected to the actual file system on the server side. And there are also in the Windows world, there's something called installable file systems that are similar to a BFS vnode framework. To make it slightly independent of the file systems, they also have similar framework. Now on the server side, it turns out that since you need high performance, it is often the case that instead of using generic machines for serving files, you might also have specific appliances and which actually do a very good or which give very high throughput. Okay? So various companies are specialized in this. NetApp is a good example of company which serves, which makes lots of high-end network attached storage devices. Now, before I conclude this particular slide, let me just mention why we are not talking currently of cluster file systems. Okay. Now, what is a cluster file system? Typically, what we refer to as a cluster file system is that you are used to the POSIX semantics on a single desktop, on a single node. So, the POSIX semantics, if you are able to provide across multiple nodes, then that will be called a cluster file system. So, now this turns out this ability to provide POSIX semantics across clusters is non-trivial, because the POSIX semantics is slightly complicated, especially with respect to failures, okay, how to handle failures in that context. Okay. Because if I try to provide POSIX semantics in the context of failures, there is going to be a lot of state that is going to be kept around and they have to be recovered when failures occur, and that is not easy. Right? So, we will actually start looking into it more systematically. I will today introduce the NFS part. I will just briefly show some of the kind of problems that are there with respect to consistency in this particular session, but in the next classes, we will start really looking at what is this consistency problem, why is it so hard, and what are the things that we can do to handle the problems. So, today I'll just indicate some of the problems, but there are deeper issues which crop up, which has to be resolved. Okay. So, there are cluster file systems available, but they tend to be more difficult to engineer, more difficult to use also, because getting POSIX semantics across clusters is not easy. So, let us look quickly at the kinds of implementations that are possible. So, normally what a simple NAS implementation will be that applications are out here and they have client NAS clients on both sides, NFS clients on both sides, and they send the request through the IP traffic, and there are NAS appliances or devices or servers which actually directly access the file systems which are stored in these disks. So, this is one simple model. A slightly more involved model, high-end model will be that instead of talking to disk, it actually talks to a storage network. Okay. So, basically here what we are doing is we are sending IP traffic here, and here you might send from these NAS appliances or servers, we are sending storage protocol traffic here. Now, this can be fiber channel, InfiniBand, or it could even be, let us say, Ethernet. Okay. It's up to us to decide what we want to do here. Okay. So from the point of the applications, they have no idea about how this is being done. All they know is that they're talking the NFS protocol or the SIFS protocol. Okay. That's all they know. Okay. So in a sense, SAN and NAS are not really, they can be quite complementary, because this part of it is handling the file protocol part of it, and this part of it is handling the SCSI protocol part of it, or the block access part of it. Okay. So very high-end systems typically are in this situation. They have both the SAN and the NAS. Of course, this is somewhat different from if you look at even larger systems like Google file system or Facebook's storage system. They do not find this kind of models that particularly useful. They want to have their own application semantics with respect to search or whatever they are doing, and so they will not go through these kind of protocols. Okay. They might still have something equivalent to something similar to this, but they might not also again use the storage protocol per se. They might be comfortable for cost reasons to use IP network everywhere. Okay. So what is the basic premise of a NFS protocol? Basically, our problem with the networks is that the networks are maybe unreliable. Because networks may be unreliable, there are some problems that show up. I send a message. It may be that the message is received by the server and it also responds, but the response may be lost. Or it may be possible that I send a request, the request itself is lost. Okay. So, and especially if you are thinking about a fairly complex network in between a client and a server, we cannot be sure where the how it can be engineered that you have the case that when I send a message, it actually reaches there and the response actually reaches back to me. Okay. It's very difficult to engineer this, and so it is somewhat easier to assume that I don't know anything about the intermediate network, and then I put all my smartness into the end devices. So what I try to do is go with this particular model, smart client and dumb server. Okay. So basically, because I can't distinguish whether a message sent and lost is because the server is not working, or the network has lost it, or the response has not come back to me. I mean, there are multiple possibilities. Okay. And from the point of view of the client, it's all the same. It doesn't matter how it happened. And it has to still do recovery. And the right kind of recovery is that if it has information about all these things, where exactly it happened, how it happened, and it can do something about it. If you don't know anything about it, the best thing is to say that it's too difficult to work with stateful protocols. Best is to assume stateless protocols. Assume that the server cannot remember what was happening previously, and somehow see if you can work around that model. And that's how NFS actually started, because if you remember, NFS started about early 1980s, and people tried to, at that time there was 3 megabit per second Ethernet, and was extremely unreliable compared to our Ethernet right now. So they were always having problems with file systems being consistent with respect to accessing some protocol which tried to give POSIX semantics. So finally people realized that providing POSIX semantics across multiple nodes is very difficult. It's not such a trivial thing. So some, let us say, careful engineers decided that you don't need to provide that kind of semantics. We provide something simpler. Okay, and that's basically what is NFS. Okay. So basically, if you have a stateless protocol, failure handling and crash recovery become that simple. Why is it that simple? Because if failure handling happens, I don't have to recover the state on the server, and so I can just when the server comes back up again, doesn't have to remember anything what it was doing before. It just comes up and it does not have to do anything. Okay. So that's one thing which is so NFS has become popular for that reason. But because it does not provide POSIX semantics, the user has to be careful. Okay? You cannot use NFS and assume that somehow the kind of application that run on a single machine will actually run on if you distribute the file systems onto multiple machines using NFS protocol. Okay, that's not going to happen. So you have to be very careful about how you use NFS protocol. Okay. So again, because NFS protocol is based on this concept of dump server. The idea here is that you have a notion of what's called a file handle. What's a file handle? It is a way in which a client can request a file. Okay. Normally what happens in Unix systems is that I have a path name, I provide the path name and then I get the file. And the thing about path name is that it has to be parsed multiple times. Okay, basically suppose I have a file name like ABCD, I have to parse A first, go to the directory corresponding to the directory slash, get A from it, then again I have to go to the directory, I have to go and look up B in it, then I have to look up C in it, so I have to do multiple directory traversals. Okay. And so it becomes a bit expensive to keep on doing it all the time. So the idea here is that somehow the server will actually, after the first access somehow, it gives me a file handle. Okay. And the file handle is used again to access it the next times when I want to access the file. Okay. So that's what is a file handle. So it's some way, in some sense, it is similar to a file descriptor on a single node system, but this is going to be across two nodes, the client and server nodes. And one of the guarantees NFS makes is that once you are given a file handle, even if the server crashes and comes up again, the same file handle I can give you the same file. Okay. In a sense, what the server has to do is to encode information in the file handle, which is opaque to the client, but it makes sense to the server so that it can look at the file handle and decide what file we are talking about. Okay. So that's one. Okay. The other thing is you have to also mount file systems. Okay. So essentially, in some sense, you have to be able to say that I need to incorporate some server file system as part of my tree structure on the client side. Okay. So what is a what is mounting a file system? I have some tree of files on my client system, and when I mount some remote file system, it has to reside at some mount point on my client system. Okay. And this particular mount semantics is there even for local file systems. We are just extending it across the network. Okay. So once you have mounted the file system, it is going to be at a particular place in the file system hierarchy, and I can traverse it just like what I was doing before. Okay. Now, because there are multiple actors when you talk about NFS, the client server and multiple processes, you also have some interesting problems. What is called the stale file handle. What is this? Basically, it may be the case that I ask for a file, I get a file handle. Before I can use it, surprisingly it gets deleted by some other party, and then that particular inode gets reused by some other party. Okay. So if it happens, then if the server has encoded that information into the file handle, then the client might get some file it did not intend to see. It is somebody else's file. Okay. Or somebody who deleted, who happened to pick up the same equivalent inode in some sense. Okay. So you have to guard against this particular problem. So the way it is done is that every inode on the server side, when it is reused again, there is something called an incarnation number which is incremented, or sorry, it's called a generation number, it's called generation number which is incremented. So any inode that is used on the server side file system, every inode has a generation number. Every time it is reused, the generation number is increased. So as I mentioned earlier, the server has to encode some information in the file handle, so that any time the client requires the file handle, it should give the file that the client expected. Okay. Now, if you want to prevent some other file to be provided as the file to the client because of the file getting deleted and being used by somebody else, you can put in the generation number into the file handle. So once you put in the generation number into the file handle, the next time the client, which innocently got a file handle and was planning to use it sometime later, it will provide that thing. Basically what will happen is that the server looks at it, sees that the file handle that has been provided to it has a generation number which is different from the current generation number. Therefore, it knows that something has happened, and the file system can tell, the server file system can through NFS tell the client, inform the client that you are referring to a file that is no longer available. It's a stale file handle. Okay. So that's the way it has to be done. Similarly, there are some issues with respect to error handling, because the errors that are happening on the other side, not on the client side. For example, there could be something like eno space. What is eno space? It is the way in which the file system tells the application that there is no available space. Okay. Again, now this is something which is happening on the other side. It's not happening on the local system. Okay. So the minute you have divided separated the client and server, the kinds of things that you are assuming in the case of a single system no longer are valid, and therefore all these issues keep cropping up. Okay. Now NFS also provides what is called transport independence. Okay. That means that it doesn't matter whether I am using TCP or UDP or some other protocol, and therefore it has to also do some encoding, etc. Okay. And it uses something called remote procedure call, which will come to which we'll discuss soon. Basically, you have a way in which each of this NFS protocol requests can be mapped to certain procedures on the server side. Okay. These are what are called program numbers, which the RPC allows it to. In a sense, every request is mapped to a particular program. For example, read or write, etc. is mapped to a particular program number, and the server actually looks at that RPC request that has come in and executes the corresponding request. That's how the NFS protocol requests get mapped to RPC. Okay. And there is a external data representation XDR, so that whatever request you are making now can go across the network and not bother about whether which operating system, which there is a type of network that is being used, whether it is based on single endian machines or big endian or little endian machines. Okay. So all those issues are taken care of by XDR. Okay. So once you have this, that means that NFS now can operate between two different nodes, and the nodes might have not much in common. Okay. For example, people have tried NFS between a Unix machine and a PC, the PC client and NFS on a server, the server being on a Unix machine. Okay. So there are a lot of intricate things that has to be taken care of, and that's why you need a lot of infrastructure, and that is at RPC, XDR, and the transport protocol itself. Okay. So let's just look at some of the typical things that we do. So what are the various protocol requests? First thing I have to mention is that NFS, if it is stateless, doesn't have an open call. In standard POSIX semantics, before you can do something with a file, you need to open the file, get a file descriptor. Here what we do is, we ask for a handle. Okay. Once we get a handle, then we can do read and write operations. Okay. The handle is got by using a lookup. So you do a lookup on a path name, you get a file handle. Once you get a file handle, then you can say read that particular file. Okay. As we also discussed in the very beginning class, I think, read and write should have an offset. Okay. It cannot go without offset, because in the case of a POSIX kind of system, the offset is maintained by the kernel. Okay. It remembers an implicit pointer, and therefore you don't have to specify where you are reading it from at the offset where you are reading it from. But in the case of NFS, this offset has to be specifically mentioned. Okay. So you have this lookup operation, you have also redirectory operations, which essentially gives you the list of files that come in. Now this actually creates certain complications, basically because once you get a list of files, I have to now iterate through all the files to get the metadata corresponding to each file. For example, suppose I want to do ls minus l on an NFS based system. First, I have to do a read directory that will give me the list of file names, and then iterate over each of the file names, asking for attributes like length of the file, etc., or the read write permissions. Okay. So, read directory is a slightly problematic thing in NFS, and it was later changed in NFSv2, for example, to read director plus, for example. So, this is the primitive that is there in NFSv2 version 2. Similarly, you have make dir, remove dir. So, there is file management, create, remove, rename. Some of those things are essentially similar to what is there on similar to POSIX. We also have there are issues regarding some interesting issues regarding some of these issues, some of these particular calls, but I will discuss it later. Okay. You can also get information about the file, get attribute. This is a very important system NFS call, basically protocol request, basically because if there are multiple parties who could be updating files, then you may want to find out if my particular copy that I have kept, suppose I am using caching, I want to know if this particular value is up to date. The only way I can do it is by sending get attribute. So, the client keeps sending get attribute calls to the server saying, please tell me what is the current status of this particular file, because other parties could also be updating it. So, this get attribute tends to be heavily used, and that is why if you look at any NFS protocol trace, you will see a lot of get attributes. The reason being that if there are multiple parties updating it, every 30 seconds or 15 seconds depending on the system, they will flush the attributes that have been cached. So, every so often you have to keep on getting requests, sending requests to the server asking what is the current state of this particular file. So, similarly there is something called StatFS, so that you can get information about the file system itself. And there is just like get attribute, you also have a corresponding set attribute in case you want to set some information on the file. Okay. Now, you also have what is called mount operations, and basically it turned out that NFS, they separated the protocol in two parts, the NFS protocol and the mount protocol. That is how they designed in the beginning. Later versions of NFS, they integrate all these things. So, basically in mount operations, you can specify what particular exported file system by the server is going to be mounted into the client file system, that is mount, you mount, and there is also a way in which you can say what file systems are exported. So, this is the high level NFS architecture. So, you will see that the application in the user space is here, and I mentioned that there is a file system independent layer, this is the NFS, the VFS layer. Now, from the point of view of this application, there is NFS file system out here. Okay. So, this VFS layer essentially will talk to the NFS client, and this NFS client in turn takes the request of the application and makes it into some messages to be sent to the RPC client, which goes across the network to the RPC server, and this RPC server in turn delivers the request to the NFS server, which talks to the local file system, talks to the local disk or whatever it is here, and then provides the response back. Okay. So, you can see that there are multiple the places where lots of things can happen. Once it may be that your failure is at the VFS layer, NFS client level, RPC level, network layer, RPC server layer, NFS level, anywhere there can be failures. Okay. So, if you are talking about a resilient system with appropriate consistency mechanisms, the errors can be in so many different places that a stateless design is actually very useful if it is possible. Okay. It turns out that a completely stateless design is not advisable sometimes. It is difficult, but it is worth doing it. That is why you can notice that NFSv2 was stateless, NFSv3 adds some state, NFSv4 is fairly stateful. Okay. So it makes sense to keep certain types of state because it helps you to actually do things more efficiently and in the ways the application is expected to be expected. In addition to this, you'll see there are two different user processes on the server side, the mount daemon and the log daemon. So the NFS client can request a particular file system to be mounted, and it goes to the mount daemon. And the NFS client also, if there are multiple parties updating this particular file, for example, there are not only the local file systems here, but there is 3 or 4 clients which are updating this particular local file system, you might require some locking mechanisms. Okay. And that's where we have something called a lock daemon. And oftentimes this log daemon is not is used. That means that somebody else is taking care of it, that no unusual let us say concurrent request take place, because that is the responsibility at some other level. Okay. Now we will look at log daemon, etc., and the issues with respect to consistency, issues with respect to failures. They are quite critical for the log daemon, and we will try to understand this at a deeper level in the next class and further on. Okay. There is a lot of complexity in this part of it. Okay. The log daemon, and we can easily see what can happen if the client takes a lock on a particular file and it dies. Then other clients may not be able to access it. Okay. So there has to be some recovery procedure, and as what we discussed earlier was that the client is stateful, but the server is not stateful. That means that since the client had the state, if nobody is able to see the state of the client, then nobody can do a reasonable job of lock recovery or whatever. Okay. It's going to be slightly messy affair. Okay. So that's the reason why you will find that a lot of NFS are used, and typically there is no log daemon being run, because the semantics are too difficult to, or generally believed to be difficult, and so people just say, I don't know what to make of it, I'll just not use it. Okay. That's often the way most systems are deployed. And that also means that NFS, you have to be careful in terms of what consistency model your application should assume when you're using NFS. So let's look at some aspects of the NFS protocol. One of them is RPC. RPC stands for Remote Procedure Call. It's a request response protocol, and ideally it should have reliable transmission. But that is not really feasible with networks, and so that's why RPC can have two types of models, what is called at least once, at most once semantics. What is at least once? That means that somehow if I send a request, it will be retried till the other party gets it. Okay. It's like your email. When I send my email to you, I would like that in case there is a problem, somehow somebody keeps retrying and sends it till finally it gets there. But the problem with that model is that it's possible that I might have decided too early that my mail has not reached you, or somebody has decided that the mail I sent has not reached you. You will retry before actually waiting for the actual mail to end up in the right place. Okay. I was too eager. I could have waited for some time more. Probably it could have made it. Because I could not figure it out, I have some fixed timeouts. I'm going to retry it one more time. So it's possible that multiple emails landed up at the same time. Okay, not at the same time. Okay, multiple emails came in. Okay. So oftentimes this multiple emails coming is not an issue, but if the multiple emails refer to withdrawing some money or something, or some such operation, that can be slightly difficult, because basically what we're talking about is, we're talking about what is called idempotency of requests. So when is idempotent? If I repeat it k number of times, it is same as doing it once. A good example of idempotent request is reading a value. I read a value once, I read a value twice, thrice, it's still the same value as long as nobody has touched it. Nobody else has touched it. So if you have idempotent operations, then at least one semantics is quite meaningful. Whereas if it is non-idempotent, then at least once semantics can be problematic. Okay. So, since file systems do have both idempotent and non-idempotent requests, you have to somehow handle the non-idempotent requests. There has to be some way to handle it, otherwise things are going to be problematic. So, some other RPCs have also at most one semantics, but the problem with this is that it means that you will not send more than one email, but your email may also not reach. That also is possible, at most once. So, it is 0 or 1. Okay. So, this is also a problematic thing. So, typically it is at least once is typically assumed, and somehow somebody else has to take care of it. For example, in the previous diagram, it could be that NFS server or the RPC server, somebody takes care of what happens if it is sent more than once, either of these. Typically, in the case of NFS file systems, NFS server takes care of it by doing something called logging, etc. Okay. Now, other thing that RPC talks about is message formats. Basically, when a request has to be sent across the network, you have to, both the parties have to understand what the message is all about, right. So, you need to essentially encode it in some format which both the parties can understand. Okay. And this turns out to be fairly tricky, because there could be differences with respect to architecture, compilers, because various compilers can do padding in different ways. Okay. They might also use different types of lengths of objects. For example, one machine can assume that integer is 32 bits, the other can assume it's 64 bits. Okay. So, there are a lot of issues that crop up when it comes to reliably saying what my offset is, or how much length of file has to be read, etc. So, there are various methods to work around it. For example, there is something called ASN.1, abstract syntax notation 1, which essentially guarantees across multiple different machines of different varieties, whether it is compiler differences or OS differences, architecture differences, network byte order differences. In spite of all of it, the sender and receiver agree on what value to be used. Okay. So, similarly, there has to be something about what is called marshalling. That means that when you have a lot of parameters, you are going to send it as a single message. So, you have to somehow figure out how to place all the objects or the parameters in some linearized form. Okay. How is that to be done? In the context of compilers having their own notions of how to do padding, etc. Okay. So, these also have to be standardized. Okay. You can also have, because now it is across the network, you need to have some authentication schemes. Either there are none because you believe that your systems are reasonably secure, or it can be Unix based. And this Unix based, basically you have this notion of UID and GID, user ID and group ID, and the assumption made is that across some departmental setting, there is administrator who is sort of managing these UIDs and GID. So, there is a consistent notion of UID and GID across all these machines, and you can essentially use that as a way to do authentication. Okay. So, again you notice that this can be somewhat of a problem, because a root on one machine should not probably be the root on the server machine, okay, if it is going to be this Unix based. So, that's the reason why oftentimes what happens is there is some kind of mapping that is done. If you claim to be root on one client machine, most machines which try to be slightly security conscious, they will map root to a null user on the server side, so that the request does not have the root permissions on the server side. Okay. So, you can also have some key based approaches or Kerberos based approaches. Okay. So, Kerberos is a cryptographic method wherein there is a key granting server and you get keys from the Kerberos based servers. Okay. So, this RPC also has got something called RPC compilers, so that your application, whether written in C language or Java or whatever it is, right, they can essentially assume that their message requests, they will get compiled to the kind of language that you are using, so that the request can be made from the language data structures that you have to the way that it has to be done in a neutral form so that it can go across the network. Okay. There are various RPC compilers out there. Okay. Also, in the case of NFS and the version 2 which came first, they also have some notion of a port mapper daemon. The reason being that initially there were no, when the standard was defined for NFSv2, where the servers listened, the ports or numbers were not standardized. So there was some way in which you had to, some infrastructure had to be provided that essentially allowed the clients to figure out where the servers are listening. Okay. So for example, the NFS server would, when it booted up, it would register itself with something called a port mapper daemon, saying that I am listening on this particular port. Okay. And so the requests that come in, right, they will have the RPC program number, and that they have to be mapped to the port numbers where they are going to be listened to. Okay. So there is some other auxiliary servers that are also needed, and this particular thing has been essentially eliminated as you go to NFSv4, for example. All these things have been taken out. Okay. Now again, with respect to the encoding, you have various things like byte ordering and whether it's big endian, little endian, etc. All those things are handled through XDR. Okay. The more involved version is ASN.1. XDR is a slightly less ambitious version of how to make sure that your data that you're sending is able to be accessed on the other side without any change in the semantics of the data that you're sending. So let's quickly look at the what are the things in the NFSv2 implementation. I should mention that NFSv1 was never standardized. So NFSv2 is the first standardized version. It has got an RFC. Okay. So what are the various components in NFSv2? It has got server and client daemons. It has got a mount daemon. As I mentioned, that's where it's a mount protocol, and the client has to talk to the mount daemon to get this particular file system to be mounted on the client side. Okay. It also needs a lock manager, and it's a very critical component if there is some sharing going on across multiple clients who are accessing the same NFS server. Okay. Now, because you are across the network, it might help to have some caching, and so there are two types of caches possible: attribute caches and data caches. Attribute caches are basically the metadata of the file, the data cache of the blocks of the file. Okay. So it turns out that if you cache it, if a particular file is being shared across multiple clients, and some of them have write permissions, then it can be the case that the attributes that you have in your cache is not the current one. Okay. So that's why you can cache it for some time, small periods of time, hoping that nobody else is modifying it. And then after a small amount of time, you flush your cached information about a particular file, and then the next time around again you try to get attributes again. So that is the typical model, and NFSv2 in the beginning started assuming that we can cache attributes for about 30 seconds. That's how they move. Now once you have attribute caches, then what you can do is, if you have data blocks, you can cache it locally, and then before you actually assume that it is valid information, you can use the get attribute information to check whether the data cache actually is valid. Okay. So what can I do? Basically, I have data blocks which have been cached. I want to know if they are still valid. So basically, I use the attribute information. I go and if I am not sure that the data cache could be holding valid information, I can send a request to the server saying, please send me your attribute of the particular file / blocks. Okay. And then I'll check it whether it is still the same as what I thought it should have been, and what the data cache that I had with me. and if that's the case, then I'll use it, otherwise I'll have to get back the data blocks again from the server. Similarly, the client actually can do, because we have this network, the client can initiate asynchronous I/O. It can get started and then not really wait till it's completed. Okay, so you can do both read ahead and write behind. Read ahead in the sense that I ask for a particular file and I ask it to give me the read ahead versions also back on the client side, or I write some things and then I cache for some time because I might again rewrite portions of it, and then at some point later I want to send it out. Okay, that is possible. Now, as I mentioned earlier, you have this problem about idempotent versus non-idempotent operations. That's why you need to have what is called server-side retransmission cache. Okay. So, what happens in this case is that let's say I get a request like remove a file. Okay. Then I tag each request with a ID number. If I see that the request comes with the same ID number, then I know that it is a repeat thing, I can drop it. So that's why I need to keep track of, so the server actually keeps track of every single request is tagged with a number. So the client is, when it retries it, it has to send the request again the same ID, that's how the server can figure it out. Okay. So, so there are things like rename, delete, remove file, all those things have to go through this particular model. Okay. So the security for NFSv2, it has you can do through, as I mentioned earlier, multiple models. You can use a Unix model or the Kerberos kind of model. Now let us look at, for today we'll just look at some of the problems with V2, and then we'll continue from tomorrow, next class, on V3, V4, then the issues that crop up for consistency, then locking problems when you are sharing, when generally we start talking about all those things, and we will go into commit protocols followed by including certain things like Paxos and those kind of models. Okay. So, okay, what are the problems with NFSv2? It turns out that it's difficult to keep Unix semantics across multiple nodes. One good example is open file access permissions. Basically, I can look up a file with a particular set of permissions, and since I am not the only person who could be modifying things, when I actually go and access it next time around, it may be that I'm denied the permission which I thought I had. Okay, that's a possibility. I can also have deletion of open files. In POSIX, I can open a file, and then if I delete it, I still can use the file handle, the file descriptor, and only when the process exits that particular blocks that are corresponding to that file descriptor, then that's the time only when it is going to be released back. Okay. So in the case of NFS, because of the statelessness, it turns out that I might have I cannot give this particular semantics. Okay. Basically because there's no notion of an open file and opening a file in the first place, because I don't have there is the open command available to me. That's one. The second is, even if I get a file handle, right, and it may be that somebody has, if I delete the file, right, then the file system on the other side will actually remove all the blocks corresponding to it. It won't let you keep it with you. Okay. So, which is somewhat different from what POSIX can do. Okay. So, this particular aspect is also not possible. So, again, for this kind of things, some workarounds are possible, but they are not complete. If the access and deletion of files happen to the same client, then the server can actually keep track of it and do something about it. Basically, it can rename that deleted file to some file name which is unlikely to be guessed by anybody, and then give that particular file as the place where it keeps the blocks on the server, and then the user can continue using it. Similarly, there is another problem here which is about atomic I/O operations. Basically here what happens is that you notice that when you do read and write, they are happening over the network, and your read and write can happen over multiple network transactions. That means that during the network transactions, you may not be able to provide atomic guarantees with respect to read or write, okay, because our network protocols cannot give you 1 gigabyte if you want, if ask for 1 gigabyte. So you might have to split it up. Once you split it up, then you will find that it's possible that you may not be able to provide atomicity that you are looking for. I think I will stop here today. I will continue from this the next time.